make. And also, I have a question for you. Let's start with that. I see that you are teaching machine learning in C#, and most people do that in Python. So could you perhaps tell something about your choice of, C#?
Yeah, so you're absolutely correct. Most machine learning courses are in Python. And as you know, all the courses I've produced so far are all in C#. So what I wanted to do with my latest course is to give something to the C# community, give them the opportunity to get an introduction in machine learning without having to learn Python, without having to learn a new language. So if you're a junior, medium, or expert level C# developer, you can take the course and just get started right away using your existing programming knowledge without having to learn Python. So I think that's a big win.
Yeah, considering how cool machine learning is at the moment, it's actually awesome that you can just dive right into the subject without having to learn a new language. Awesome. All right, so just regarding the practical announcements, we will be together for about 1 hour, and Mark will be talking for, let's say, 40 to 45 minutes, after which he will be answering between 5 and 10 questions, depending on the time that we have left. And regarding those questions, if you go to the Zoom menu, you will see that Mark is the host and that I, Sonsoles, am the co-host. So if you have questions that you would like to have answered, please send them to me, Sonsoles, the co-host, and not to Mark. But he will cover them himself, of course, once he is done with his talk. In case that there is no time for your question, you can also join Mark's free Facebook group called C# Architects, and I'll be putting the link in the chat just in case that you need to check that later. And as I said, you can post your question there and Mark will be happy to answer it for you. So yeah, without any further ado, I now give the word back to Mark. I look forward to it. Go ahead.
All right, so I'm going to try and pack everything that I want to talk about in 40 minutes. We're going to cover a lot of ground, so I might have to talk a bit fast. So if things are going a bit too fast for you, if you see me introducing a concept and you know it's gone, I've already moved on to something else before you can blink, then I invite you to enroll for my machine learning course, because everything I'm going to show you in this webinar, all the theory is in the course, and the course gives basically a complete foundation, a complete theoretical foundation to, well, basically to understand everything that I do in this webinar. So I invite you to check that out. I would also like to mention in another course, so this is a really awesome masterclass by our very own Sonsoles. It's a masterclass called How to Break Free from the Assembly Line. So if you are a team leader or you're a startup founder and you're asking yourself, how do I choose the right people for my team? And I know I've asked myself that on many occasions in the past. That you can register for Sonsoles Masterclass. So it's called How to Break Free from the Assembly Line. And you can find it on our website, sonsolesalonso.com. If you go to our website and you look at the main menu at the top, there's this huge link that says Masterclass. Just click it and you'll go to the page. And while you're there, you can also download the Modern Leaders Team Collaboration Roadmap. So this is a free PDF that will teach you 8 steps for awesome team collaboration.
So, wow, okay, Mark, that's very kind of you. Thank you for doing that. Since you mentioned it, would it be okay for me to put those links in the chat as well?
Sorry, I was fighting my mute button. Yeah, that's perfectly fine. Go ahead.
Okay, great. So yeah, go right ahead. I look forward to it, as I said.
Okay, so let's get started. So welcome to this webinar. Let me just change a few things on my desktop. Here we go. So the first thing I would like to talk about is what is machine learning. So if you haven't, if you're not up to speed yet on machine learning is a completely different way of programming. So like in the past, you used to write software where basically the code is one big bunch of if then else statements, where we're putting all the logic up front in the software. Machine learning turns that completely on its head. In machine learning, the software figures stuff out on its own. So initially, a machine learning algorithm, or model as we call it, produces random results, completely random. And the idea is we run the software and there's always a feedback loop. So we tell the software if the answer is correct or incorrect. That's called supervised learning or supervised training. So when you run such a training loop, you're constantly telling the machine learning algorithm, this answer is incorrect, this answer is terrible, this answer is great, hold on to that. The next answer is terrible. So you keep giving this feedback, and the machine learning algorithm uses that feedback to train itself and produce more and more accurate results. So this is pretty awesome because the machine learning software can basically find new patterns and correlations in input data. It can discover completely new patterns that people haven't even thought about yet. So machine learning is pretty cool because it learns from experience, so it gets smarter and smarter, and it can deal with new situations. So we can actually build software. We can train the software with data that we have in advance, data that we have up front that we know about, and then we can deploy the software in an environment where it's in a completely new environment with completely new data, and it can figure out what to do with that new data on its own. So this opens up software development for entirely new domains. For example, think about satellites or robots in outer space, which encounter completely unanticipated situations, and they're intelligent enough to figure stuff out on their own. So this is really cool stuff. If you want to use machine learning in C#, there are a couple of frameworks you can use. In this webinar, we're going to use the Accord framework, accord.net. If you have seen my computer vision webinar, then you're aware of this framework because we use it there as well. Accord is fairly broad. It can do computer vision, it can do machine learning, it can do statistics. It's a very nice generic mathematical framework for C#, and it's completely managed code. Accord is written in C#. The source code is on GitHub. So you can just go up there and check it out, download the source code and compile it on your own. So completely managed code. Another great machine learning framework is the Microsoft Cognitive Toolkit, CNTK. This is Microsoft's answer to TensorFlow. It's pretty awesome. It's faster than TensorFlow. It's really good performance. So it's the fastest machine learning framework out there right now. The disadvantage is in the past you had to use Python to use it, but Microsoft has recently added C# APIs to this library. So as of now, basically, we can use C# code for the Cognitive Toolkit. So one of my next courses on machine learning will definitely be about this framework. Finally, we have TensorFlow. So TensorFlow is from Google, Google's machine learning framework. They were basically the first to market with a good framework. Now, you can use TensorFlow in C#, but that's why I put the warning triangle there. TensorFlow, you can only consume pre-trained neural networks with C#. So TensorFlow has this massive API for training neural networks, creating and training neural networks, but they have not been ported to C#. There's this project called TensorFlow Sharp, but it only covers the bindings for using pre-trained networks. So if you're a C# developer, that's a disadvantage. All right, so here's the challenge for today's webinar. I am going to write an app, or I'm going to demo an app because I wrote it already, that reads in handwritten digits. scans of handwritten digits, and it converts them to text. So basically, it does optical character recognition on digits. So I'm going to use a neural net. I'm going to train it on a training set of digits, and then it's supposed to correctly translate these images of handwritten digits to well, to ASCII, basically, yeah, to the binary form of the digits. Now, the quality is terrible of this data set. If you look at some of the digits, I'll be showing you some of them later. Some of them, they're completely incomprehensible. It's like impossible to tell if it's a 7 or a 1 or an 8. So it's really, really bad data. So we're giving the neural network quite a challenge here. So I'm going to use a neural network. This is what a neural net looks like. So this is a very simple neural network. You can see it has like 3 columns, and every column has 3 nodes in it, except the last one, which only has 1. So a neural network is just a special case of linear regression. So it's basically a very advanced form of linear regression. On the left, we have the inputs. We call those features. So these are nodes, 3 input nodes. And we present input data to these nodes. Now, a node can read in data is commonly between 0 and 1. So a node will read in a double, and it's a value between 0 and 1. We can have as many nodes as we want in a layer. And then you can see that all these input nodes transfer their data to a hidden layer. There's a layer in the middle. So this is a layer with, again, 3 nodes. Now, these nodes have an activation function at the end. So this is a function that transforms the output of a node. So you can have all kinds of activation functions, and they very subtly influence the behavior of a neural net. We're going to use an activation function in this webinar. Now, finally, there's an output layer with 1 output node. We call that the label. That's why I put an L in there. So this is basically the output of the neural network. So this neural network would read in 3 different values, 3 doubles, and then it would produce 1 double as an output. So it is a very basic example. You can see that the layers are fully connected. So the features are fully connected with the hidden layer, which means that every node in the one layer connects to basically every node in the next layer. So that's the arrows. Those are the connections between the layers. So let me show you the neural net that we'll be using in this webinar. It looks like this. So it's a bit more complicated. So what we're going to do, we're going to use a neural net with 2 hidden layers. You can see the yellow and the green layers in the middle. Those are the hidden layers. These hidden layers have 100 nodes in them. 100, so that's quite a lot. The input layer at the left side has 784 nodes. And it's 784 because I'm going to feed this neural network scans of handwritten digits which are 28 by 28 pixels. So 28 times 28 is 784. So you can see how this works. Every single pixel in the input image is presented to a unique node. So all I have to do is convert those images to monochrome, convert the pixel value to a value between 0 and 1, and then present that value to an input node. And that's how you present images to a neural network. So then the data will flow from left to right through the network. It will go through the 2 hidden layers with all these interconnections that will process the data. And finally, we have an output layer, and you can see there's 10 nodes in the output layer. Now, these 10 nodes correspond to the digits 0 to 9. You can see I've labeled them on the right. So the topmost node, called L1, it will activate when the neural network thinks that it's looking at a 0. The L2 node will activate when the network thinks that it's looking at a 1, and so on. So with 10 output labels, 10 output nodes, we can predict the digits 0 to 9. Now, these values on the output will be doubles. It will be numbers again between 0 and 1. And these are probabilities. So the idea is the neural network gives us confidence values for all the 10 digits. It's basically saying, I'm 90% confident that this is a 2. I'm 9% confident that it's a 1. And I'm 1% confident that it's a 7. So the probabilities would add up to 100. 100%, and we get this array of 10 probability values. So it's very cool to see how the network is thinking and how it's trying to match the input image to one of these 10 digits. Now, last thing, you can see that the last three layers in the neural network have a sigmoid activation function, sigmoid activation. Sigmoid is just a mathematical function that we slap it basically at the output of a node in a layer, and it transforms the value. And the nice thing about sigmoid is that it takes any input at all, and it transforms it into a probability. So when you create a neural network and you put sigmoid activation functions on all the nodes, then basically the output of the neural net will be probabilities. And that's exactly what we want here. We want the network to tell us, I am 90% confident I'm looking at a 2. Okay, so here's the process we're going to be following. We are going to create a model. So this will be the neural network, and we're going to train it on training data. I'm going to load different data files and take 80% of the data that I'm loading, and that will be for training. And then we're going to test the network with validation data. So the validation data will be the final 20% of the file that I'm loading. So this is, again, a common trick in machine learning, that we load a data file and we basically partition it into two pieces, 80% for training and 20% for validation. And we're going to do a training loop. So we're going to incrementally improve the model by optimizing it to the training data until we have an output that looks good. Then we're going to take that model and run it on new data. I'll show you what that means when we reach that point in the webinar. So I'm going to use the model for something cool. So let's get started. I'll drop right into the code. Let's do this update another time. So I'm going to drop right in the code. I'm using a library called Deedle, which is awesome for handling data sets. So this is a console application called Handwriting Trainer, which will train the neural network. And the first thing we're going to do is just load CSV data. So this file, handwritten digits small, is the input data. I'll show it to you. So this file, it's just CSV, yeah, comma separated values. The first column is the digit. So this row is all about the number 6. Then the next columns are pixel values. So these are the values of the pixels in the image, going from left to right and top to bottom. So this will be a 28 by 28 grid, written as one long array. So it's 784 numbers. Now, if I scroll to the right, then you can see that eventually, there are some numbers appearing here. So these would be non-white pixels. So the format here is that white pixels are 0. Black pixels are 255. So here's 252, it's almost black. And so these are basically monochrome images. So these are lots of values in between. So this is how the data has been formatted. And I've got loads of this data. What you're actually looking at is a famous data set called the MNIST dataset. It's a set of 60,000 handwritten digits, 60,000. And it's a classical data set for training machine learning systems. So we're going to use that here. This file only contains 100 of those 60,000 images, because training the full set, believe it or not, it only takes 4 minutes on my MacBook Pro. That's without a GPU. So that's still pretty fast, but it would take too long for this webinar. So I'm going to demo the code with this small file. So the first thing I'll do is I load the digits into a Deedle frame. So it's right here. Then the next thing we have to do, we have to normalize the pixels. So I said before that neural networks love to handle data between 0 and 1. These are pixels between 0 and 255. So the only thing I need to do is just divide the columns by 255. So you can see that Deedle is really powerful. You can use this frame and then use these square brackets to index into a specific column, and then you can use it into an expression right away. So I'm dividing all the values in this column by 255. So this is typically how you would program in Python, and with Deedle, now it's also possible in C#. So to show you what that looks like, I'm going to grab a random digit from the data set. So here you can see I use a random number generator to grab a random row from the data file. And then here I'm extracting the value of column 1. So this will be the digit that I'm looking at. I'm putting it in this variable. And then I'm generating these arrays. So these are arrays that I need to plot the digit. So basically, I'm just looping between 0 and 784. And I'm using modulo 28 and divided by 28 to basically treat this as a 28 by 28 grid. And then I'm indexing that data right here. I'm putting it in my X and Y arrays, and then I'm using the scatterplot function of accords to create a plot. So let me just run this so you can see what that looks like. So basically, I'm just loading the CSV file, and then I'm grabbing one random digit from the file and plotting it. So here we go. So here's one image from the file. So this would obviously be a 7. So, you know, it's completely random. If I run it again, we'll see a different digit. So this is how the data is presented to us, this 28 by 28 grid of numbers. So let's move on. The next thing I need to do is neural networks like to work with values between 0 and 1. And if you recall the data file, I have this little problem with this first column. The first column is the digit that we're looking at, and it's not a value between 0 and 1. So what I'm going to do here, I'm using a little trick to create something called one-hot encoding. One-hot encoding is that I basically create 10 extra columns in my data file, 10 extra columns, and every column will have a 1 in it if we're looking at the digit corresponding to that column, and it will have a 0 in it otherwise. So this sounds a bit convoluted, so I'm just going to run the app so I can show you what that is actually doing. So again, one-hot encoding is a very popular trick in machine learning to prep data for using a neural network. So these are the columns that have been generated. So you can see here, the first row is the number 6, and then we get all this pixel data about of the image of the number 6. Now I've added 10 columns to the end of my frame called label 0 to label 9. And if you look in label 6, you can see here's a 1. So all the others are 0, and label 6 is 1 because this is the number 6. The second row is an image of the number 5. And now label 5 contains a 1, and everything else is 0, and so on. So here's a 7 in row 12, and label 7 has the 1, and everything else is 0. So this is called one-hot encoding, and this is how you would feed an integer into a neural network. You would create separate columns for every individual value that this integer could be, and then you put a 1 in the corresponding column and a 0 in all other columns. So one-hot encoding. We need to do this to properly train our neural network. All right, then the next step. So I told you about training and validation. What we're doing here is I'm taking this frame that contains all of my data, and I'm calculating a pivot point. So this is where the training data ends and the validation data starts. I can see it's just the number of rows times 0.8. So the first 80% will be training and the final 20% will be validation data. And here's how you do it in DDAL. So you can just say frame.rows, and then you put an enumerable range into this array index. So this will create a new frame called training, which contains the first 80% rows of the original frame. And I can do the same thing here. I can create a range that starts at the pivot point and goes to the remainder of the set. So that will be the final 20%, and that goes into validation. So super easy in DDAL to basically slice and dice frames in rows and columns. Okay, so now let's set up the neural network. So I'm going to create a neural network, and it's going to read in the pixel data. So the pixel data is column 2 up to column 785. So column 2 and then 784 columns in total. So I'm creating this range, and then I'm creating it's basically a string array with the names of the columns that contain the pixel data. And for the output of the network, I'm doing the same. I have this range going from 0 to 9, starting at 0 and 10 items in total. And here I have these label columns. So this will be label 0 to label 9. So you can see that the pixel columns are the input, and those one hot columns I just created are the output. Now with these two lines of code, I can very quickly index into the training frame and grab these columns. So you can see I use this columns property, and this is the string array. So that gives me a subset of columns. And then I can say, to array 2D, that will project it into a 2D array. And then I can say to jagged, which will produce a jagged array. So with this single line of code, I create a jagged array of double values, which contain all the values in this set of frame columns. So this is literally the input data that the neural network needs to train on. And for the outputs, I can do the same thing. So here I use the label columns. So you can see this is a jagged array of doubles, and this is also a jagged array of doubles. So now we have our arrays to feed into the neural net. So let's create the neural net. I'm using the Accord library to create the neural network. And if you want to build a neural network with an activation function, it's simply called activation network. So you can see I put in my sigmoid function so that I get probabilities as output. And these are basically the layers. So I have 784 inputs. Then I have 100 nodes in the hidden layer. Then I have another hidden layer with 100 nodes. And then I have 10 output nodes. Now here I use a learning algorithm. So I need to train my neural network. And there's a famous training algorithm called backpropagation. So I'm using that here. So basically, I'm telling Accord to train this neural network with backpropagation. And then here, I train the neural network. So training, again, is super easy. In a loop, the only thing you need to do is run this line. So the backpropagation object has a method called run epoch, and that will train the neural network during one iteration. And it will return an error. It will also adjust the neural network to reduce the error, but only in a single step. So usually what you do is you just run this code in a loop for as often as you like. You can see I'm running it here 50 times. And the error will slowly decrease. So the backpropagation algorithm will slowly optimize the network more and more and minimize the error as much as possible. Now you can see I'm throwing the errors into a list so we can track them. And finally here, I'm creating a scatter plot of the errors. So I'm running this neural network, I'm training it 50 times sequentially, and I'm plotting the error values one by one. So let's look at what that looks like. So here's the random digits. Here are the one hot columns. So this is the training loop. You can see 50 iterations. You can see the error slowly decreasing. And this is, we call it the training curve. So this is how the neural network gets more and more accurate over time. So you can see the y-axis is probability. So initially, the network is random. So it has a 50% probability of being right. And you can see the more and more I train it on the training data, the more accurate it gets. And at the end, we're at 0.008. So that's a pretty good error rate. That means that the network will be 99% accurate, if I'm reading this correctly. That's a fairly good result on training data. So that's the training curve. Then the next thing I can do is I can validate the neural network. So I've got this trained neural network. I can now feed it the validation data. And I can use the network to compute the predictions on the validation data. That will give me an array of 10 doubles, which are the predictive values for the digits 0 to 9. I can use some link ninja moves to get the highest prediction. And then here, what I'm doing is every time when the network is wrong, so if it's incorrectly classifying a digit, I print the output on the console. So I print these 10 prediction values, and then I show the highest value, so what the network thinks is the digit, and I compare it with the actual digit so that we can basically see how the network is doing. And I print this wrong on the console because it's incorrect. I'm also creating a list of mistakes, so we can use those later. So then, finally, at the end, I plot I print the total number of mistakes. So this is the total number of mistakes that the network made, and the accuracy. So the accuracy is just the total number of validation data, the number of mistakes divided by the total number of data in the validation. So that will give me a percentage of how accurate the network is. And then I use the same code we used earlier to grab a random digit. I'm going to grab a random mistake from the set of mistakes and plot it. So we can take a look at what a digit looks like that the network has difficulty recognizing. So let's run it and see what happens. So here we go again, reading in the data, normalizing pixels, plotting a random digit, 1 hot encoding, 50 training iterations, the training curve, and okay, I'm going to put this one here and this one here, so we can take a look. You can see that so there are 5 mistakes. So the accuracy of the network is 75% because it's training on 20 records. So here you can see the probability values. So the highest probability here is number 7, 82%, but the number was actually a 7, not a 9. So this is wrong. And you can see here that the network, it has 79% probability for the number 3, but it's actually the number 2. And you can see 2 is only 0.01%. So the network is not very well trained yet. You can see here we have a 0, and the network thinks it's a 5, see 0.63, but it's actually a 0. And 0 is actually 42%. So this one isn't bad. 42% the network thinks it's 0. 63% the network thinks it's 5, and it turned out to be the 0 after all. So you can imagine with a bit more training, these two values would flip, and the network would be correct for this record. And here you can see an incorrect prediction. So this squiggle, the network thinks that it is a 6, and it's obviously, because it thinks it's like the bottom part is part of the 6, the curve of the 6. So the neural network has picked up this curve here, and it has associated it with the number 6. But what it hasn't realized yet is that a 6 doesn't have this bit up here. So the network isn't sophisticated enough yet to realize that this isn't a 6. So now let me run this code again, and I'm going to use a bigger data file. I'm not going to use the biggest one because it's simply too large to run now, but I'm going to use the medium one, which has 1,000 records. And we'll just run this whole thing, and then we can take a look at the results. So there we go, compiling, reading data. It's going to take a bit longer. Here we go, normalizing. You can see everything is a bit slower. So here's a random digit. That's obviously a 6. 1 hot encoding. And you can see now we have 800 records. So the training is a bit slower. You can see the training epoch 0 starts at 45%, so it's almost random. And now it's slowly dropping. 50. So here's the training curve, which looks nice. So here's a prediction. So the network again makes that same mistake. It thinks this is a 6, and there's a lot of 6ness in this image, but it hasn't realized yet that this thing at the top makes it an 8 and not a 6. So you can see how the neural network is starting to recognize shapes, curves, and features of digits, but it's not good enough yet to accurately predict everything. Now here, if you look at the output, you can see here these are the incorrect predictions. 27 mistakes out of a total of 200, which is an accuracy of 86.5%. So before we had 75%, now it's 86.5. So the accuracy has gone up. So that's pretty awesome. Now I'll show you one more thing. Usually when we do a training, we don't do the whole training and then we do the validation at the end. Instead, what we do is we do the validation during the training. So while we are training the network, we run a single epoch to train the network, and then we immediately validate this network, and we save the validation error. So when we do this in a loop, we get a training error, and we get a validation error. And that's really cool, because we can compare the two, and we can derive some interesting conclusions from that. So here I've got another block of code that will plot the training error and the validation error in the same curve. So I'm going to run that. So let's run this again. So 1,000 digits, 50 training iterations. So here we go, normalizing pixels, picking a random digit. That's obviously a 2. 1 hot encoding, and training. So now you can see the training is a lot slower, because I'm validating the neural network during each training iteration. So I have to do 50 validations. But keep in mind, this is running on a MacBook Pro. This is Windows 10 in a virtual machine. And my MacBook has a very old Intel graphics adapter in it. It's not fast enough for machine learning. So I'm not even using a GPU. This is pure virtualized CPU performance. So if you run this on bare metal on a Windows machine, it'll be much, much faster. And this is what I wanted to show you. So this is the training and validation curve for this neural network. So the important thing to realize here is you want to see the blue line below the red line. Blue is training error, red is validation error. Neural networks, they always look like this when you train them. The validation error is always a bit larger than the training error. If those two lines flip over, if the one is below the other, then it's an indication that there's something wrong with the data or with the code. Another thing you should be on the lookout for is if the validation error starts to rise. So that happens sometimes, that the red line will start to go up. So the area between red and blue will start to increase over higher epochs. When this happens, it means that we're overfitting. It means that we are creating a neural network that is superbly attuned to the training data, but it's so well attuned that all the random noise in the training data, it thinks that those are features. So it has learned to recognize the randomness of the training data. And then, of course, if you feed it different data, like the validation data, the random noise will be different, and the prediction probabilities will be terrible. So this happens a lot in machine learning. It's called overfitting, and you don't want that. When you plot these curves, the training and validation curves, you should always be on the lookout that when the errors stabilize, that both lines remain parallel, and that not that the validation error suddenly starts to increase while the training error keeps dropping, because that always means overfitting. Okay, so that's training. At the end of my code, the last thing I do is I'm saving the network. So you can see I use a serializer, and I just save the neural network to a file. I'm doing that because now we can actually use this neural network in another app. So I'm going to show you the second app. Let me close this and close this. So the second app is really simple. It's a picture box, 640 by 640 pixels. And I've wired up the mouse events, so I can just use the mouse and scribble on it. As soon as I let go of the mouse button, it will use the neural network and try to predict what I've drawn. So I'll show you here's the loading code. So you can see this is, again, I use the serializer to load the neural network from a file. So this will give me the pre-trained neural network, and I can use it right away. And then here, this method will construct a bitmap, a 280 by 280 pixel bitmap. It will draw my doodle on the bitmap. It will resize it to 28 by 28, because that's what I trained my neural net with. It will get the pixel data of this bitmap. So that gives me values between 0 and 255. It will scale the pixel data, and it will flip the color so that white is 0. And then it will run a prediction. So this is how you do that. You take the network, you call compute, you feed it the pixel values, and you get back the predictions. Easy as pie. Finally, what I do here, I've set up 10 progress bars in the app. So basically, I'm just going through the predictions, and I'm filling in all the progress bars. So let's run this and see what happens. So bear in mind, I'm initializing this app with a quick and dirty training file. So a training file trained on 1,000 records. That isn't enough for good recognition quality. If you want really high quality handwriting recognition, you need at least 3 hidden layers in your network. You need to have 300 nodes in the network, not 100. And you probably have to train for way longer than 50 epochs. So we're going to see some pretty bad quality here, but this is purely for demonstration. So let's get started. I'll draw 3. Yay, awesome. Okay, now 4. See, so this is typical. I mean, this could be a 7 or a 9. It kind of looks like that. You can see that it's picking up this curve here. So it's not good enough. So let's do it like this. Nope, still thinks it's a 7. Like that. Nope, it thinks it's an 8. So you can see the number 4 has been written in a specific way in the training data. Here we go. Now it's picking it up. So this is how the 4 looks like in most of the training sets. Let me try an 8. Number 2. You can see how that can happen. Like you have this 2 curve here and then down here. You know, it could be a 2. So let me try again. I'm just going to try different ways of drawing the 8. Here we go. So it thinks it's a 5, and again, it could be a 5. I mean, there's more data in here, but the 5 is definitely in there. And you can see that it's starting to realize that this is an 8. So, I mean, it could also be this, that 8s are always drawn like that with a small top. Nope. Maybe the other way around. Nope. So you can see it's recognizing the 0. That's good. So it has difficulty with the 1. I always get a 7 when I try a 1. 1. Hey, here we go. So a lot of 1s have been written cursively in the training set. So you have to draw it like this. If I draw a straight line, you can see now it's getting confused. So this is pretty awesome. See, that's obviously a 9. Let's try 6 the same way. Whoops, messing that up. Like that. Nope, 0. Let me close the 6. Try that. Nope, that's a 5. Let's do it very sloppy like this. Up. There we go. So you can see that the digits in the data set are creatively drawn, to say the least. We can also kind of get a clue here of what the network is picking up. So 6ness obviously means like a slow curve and then a quick doodle down here. So any number I haven't tried yet? 5. 3. Let's make it a bit bigger. 5. 7. Nope. Here we go. So if you think the recognition quality is low, yes, that's true. But the reason is I'm using a quick and dirty data file. I'm using a neural net that was only trained on 1,000 records. And one thing that's very important, I need to present my numbers the exact same way as I did when I was training the data. So I've been using the training data, but now I'm basically just doing free-form drawing on a canvas and presenting that data to the neural net. Now, one thing about neural networks is they are incredibly sensitive to position. So what that means is if I draw a 5, I can train a neural network to recognize a 5 like this, but if I draw a 5 like this, it's going to have difficulty recognizing it. And if I draw it like this, same thing, see, it thinks it's a 2 now. So there's a huge difference where the 5 is on the canvas for it to recognize it. So neural networks are really, really sensitive to positional information, to transformation. So the amount of margin around this number is pretty important, and it controls the accuracy of the network. This is actually a big open issue in machine learning. People are trying very hard to create neural networks that are translation invariant. So they basically only focus on the geometric of the feature, and they ignore how large the feature is, and where it is on the canvas. But so in a nutshell, this is how you create a neural network that can recognize handwritten digits in only a few lines of C# code. So let me stop this. So that brings me to the end of my story. So I'd like to focus your attention on the machine learning course that I created. It's called Introduction to Machine Learning in C#. It's only $47, so it's actually not that expensive. I think that's a steal, personally. And this course will teach you, it will give you a complete foundation in machine learning. So it starts with linear regression, which is the simplest form of machine learning. And then it builds up and up and up. It goes to logistic regression, it builds up and up. It teaches you about feature engineering, that is transforming data for neural networks. It tells you how to optimize regression algorithms, and it ends with deep neural networks. And it contains this coding exercise that you just saw. So the course takes a deep dive into the code, and it explains every single bit of code that I just showed you, and it shows you all the theory behind it. So what are neural networks? How are they derived from simpler linear regression? Why am I normalizing everything from 0 to 1? What's the whole theoretical foundation behind neural networks? So if you take the course and you will go through it, it's about a week of content. It's 40 lectures, so it will take you about a week to go through the whole thing. When you take the course, you will have a pretty good foundation in machine learning, and you will be able to do everything in C#. So if you're prepping for a machine learning job, if you're preparing for a career move into machine learning, this will give you a pretty good foundation. You can definitely you can definitely carry your weight if you have to talk about machine learning, if you have to evaluate algorithms, if you have to look at some code. With this foundation, you can definitely pull your weight. So again, I invite you to check out the course, and if you like what you see, to enroll. So finally, let me show you some info about me. So my name is Mark Vrager. I specialize in hardcore tech solutions. I like to say that I take your tech leadership to the next level. And for me, tech leadership is hard and soft skills. So these were hard skills that we covered today, like really advanced technical knowledge, like machine learning and neural networks. But I also focus on soft skills, like how you can become a great tech leader, how you can become a great CTO, how you can manage a team of developers, how you can prepare yourself for the role of solution architect. So I've got a ton of courses on my website about hard and soft skills to take your tech leadership to the next level. There's also a Facebook group called C#.architects. If you're not already in the group, I invite you to join. That's where we all hang out, and that's where I share cool new nuggets of info. And I'm also on social media, on Facebook, Twitter, and LinkedIn. So if you like to contact me, please don't be a stranger. You can contact me in the Facebook group, or if you want, you can even drop me an email. Yeah, and that brings me to the end of this webinar. So I'm interested to hear if there were any questions. So Sansolis, I'm going to give the word back to you.
Awesome as always, Mark. Thank you very much for all of this. I actually put a message on the chat because I didn't see any questions coming, but so I'll just post it now. My own question to you guys. Do you have questions for Mark? And if so, can you put them in the chat? We have about 10 minutes left. I see someone typing.
Yes, someone's typing. Awesome. It's always painful if there are no questions, you know. Thank you, whoever is typing. You saved us.
Oops, the person stopped typing. So anyway, let me see.
It'll come back. I'm optimistic.
So guys, Mark loves answering very difficult questions. So here is one from Greg. He says, how good is machine learning for comparing two names? like Bob Smith and Robert Smith as a match?
Pretty good, actually. You can definitely use it for that. There are different algorithms you can use. So you can train a neural network for what words sound like, so that if you have two versions of a name and you want to group them close together, you want the neural network to say these two are related. You can train a neural network to realize what names sound like, and then group them by that. What you can also do is train a neural network on common mispronunciations. So if you have Smith, Robert Smith, and you have another, you have a typo basically, and someone is called Robert Smith, S-M-I-T, without the H at the end. You can train a neural network to learn that that is a very common misspelling of Smith, and then combine them again. So you could train a neural network to say, this is a cluster of misspelled names or names that are closely related to the name I'm interested in. Teach the network which name is the correct one, and then it will automatically associate misspelled names with the correct version. So basically, you can train a neural network to correlate any kind of data. So yeah, this is definitely possible.
All right, I have another question. This is Nelson. He's asking, is one-hot encoding very common, or can other encoding algorithms be used?
One-hot encoding is really common. It's like the go-to method for encoding numerical values. One-hot encoding, it's gigantic. Huh? In the course, we're doing one-hot encoding on latitude and longitude. So we have the state of California. We take the latitude and longitude of coordinates in California, and then we create a one-hot encoding vectors. So basically, you create a grid and you overlay it over the states, and then every grid cell gets its unique column. So it's very common to have hundreds of one-hot columns, and the really big neural networks have thousands and even millions of columns, millions. So crazy. So one-hot encoding is really common, and I think the reason is because neural networks that process data as numbers between 0 and 1, or sometimes you also see -1, between -1 and 1, those perform really well. They converge well, they produce fairly accurate results, and so if you restrict yourself to the range between 0 and 1, one-hot encoding basically is the go-to method to convert input data into that representation. So yeah, to answer your question, it's very, very common.
Okay, so Greg, who asked the previous question, he says, great, thanks. He's happy with your answer. And I have a couple more questions. One of them is, do you have a GitHub page with this code or other code?
Yeah, I have a GitHub page. Big surprise, it's called MD Farger, just like all my other social media accounts. Right now, the GitHub page has my computer vision code on there, nothing else. But I will be uploading this source code to GitHub. And what I also do is I'll put this webinar online, and I'll put a little thingy underneath there where you can get the source code. So I will make sure that you can get the code.
Okay, so Nelson says, also from the previous question, your explanations are very clear and precise. I appreciate your teaching style. Thank you.
Wow, thanks. Thank you, thank you. I'm doing a little bow here. You can't see it, but thank you. You're too kind.
I have one more question here. What if you have missing data? Is a question from Rick.
This is it's an awesome question. Thanks for asking that. So missing data, that's really interesting, because you can have two kinds of missing data. If the complete record is missing, then there's not much you can do. Then you cannot train on that data, and the data would show up later when you use your network in a new scenario. But what you can also have is that you have features but no label. So you have the inputs, but you don't have the outputs. And in that situation, you can definitely add that data to your training and your validation set. But of course, you can't steer on that data. You can't tell the network your prediction for this data point is incorrect. But you often see people adding data with features but not labels to their training set, just to make the network acquainted with the full range of data, even though the labels are not all there. If you have the other situation, if you have a label and no input, again, that's kind of difficult, because then you don't know what to feed into the neural network to get that output. So that's not a very useful record. But having input features but no output label, that's very common. And in fact, there is a subdomain of machine learning called unsupervised training. So unsupervised training, where you have input data with no labels. So you have the inputs and you don't have the outputs. So the example here would be, we have all these images of handwritten digits, and we do not have the first column. So we don't know what the digits convey. You can actually train a machine learning system on that data. And what the system would do is it would cluster the digits together. So it would learn to recognize similar digits and cluster them together into buckets. So if you would feed that network a new digit that it hadn't seen before, it would basically say, I am 87% confident that this digit belongs in bucket number 3. The network has no idea what bucket number 3 means. It's just one of the 10 clusters that it created on its own. But it's basically just telling you, I see this digit, this image, and I think it's closely correlated to these other images. What do you think? So this is called unsupervised learning, and it actually works. You can train machine learning data, you can train machine learning models on unlabeled data, and they can actually produce useful predictions, even though the network has no idea what the actual truth is. So that's pretty awesome.
Okay, great. I see a number of thanks come in, one from the mysterious CA and another one from Bernd. And we have about 2 minutes left, so maybe we can squeeze in one more question in there. Anyone? Any takers?
Last chance, guys. Come on. Ask me anything.
Okay, so anyone? At the count of 1, 2, 3. No, it seems no more questions. Oh, yes.
It's like an auction, huh? Like there's a hammer going down. Going once, going twice.
Exactly.
Okay. This one.
We have one more question again from the mysterious CA, who says, tell us more about CNTK.
Yes. So CNTK is my favorite machine learning framework. CNTK blows Accord out of the water. It's way faster. It also runs in Azure. It runs in the cloud. So if you create CNTK neural networks, you can upload the training into the cloud. And of course, Microsoft loves this, because to train a large neural network, you need like loads of virtual machines and lots of GPUs, which you have to rent, of course. So they like it. But it's a nice idea, right? You could actually create machine learning software on a mobile device, and then you just upload the whole training into Azure, and then the trained neural network flows down again into the mobile phone and is used locally. So you can basically train neural networks on hardware that wouldn't support training normally. So CNTK is Microsoft's response to TensorFlow. TensorFlow came first. Google, they basically cornered the market in machine learning by releasing TensorFlow. And Google selected Python as the go-to language for machine learning. So because TensorFlow uses Python, everybody's now using Python. And TensorFlow is like, it's everywhere. So Microsoft looked at TensorFlow, and then they created their own framework. But so here's the cool thing, they created a better framework. So CNTK is faster than TensorFlow. It's much faster, but it's also more forgiving for badly formatted data. So the question we had earlier about missing records in the data file, TensorFlow completely trips up if your data series, are not all the same length. It will produce basically garbage data. CNTK can actually handle this. It will align the series so that the missing data is just like holes in the data. So it will actually make sure that your data series line up. If you have to do this manually, it's a lot of code that you have to write, and CNTK automates it for you. So I really like the framework because it's the fastest machine learning platform out there right now. It has cloud capability and it aligns data for you. The go-to language for CNTK in the past was also Python. So Microsoft launched it with Python bindings because, of course, they wanted to have all these machine learning developers who are used to programming in Python, and they want to bring them into the Microsoft camp. But now they've also added the C# bindings. So you can actually use C# to train CNTK networks and to use them. So that's really awesome because it means that the fastest machine learning platform on the market right now is something that we can use in C# directly. I think if you're a C# developer and you're interested in machine learning, you definitely have to know TensorFlow because you might encounter it in your work. But there's nothing wrong with telling your employer, telling your boss, I recommend that we use CNTK because in a .NET environment, it's just the best solution. So yeah, you can tell I'm pretty enthusiastic about the cognitive toolkit. I really like it.
And is it open source, Mark?
That's a good question. I'm not sure. I need to check.
Okay.
Yeah.
So there was another question by CA, and we are now. It is now 2 minutes or 6. So I think we are done for today.
Yeah, let's wrap this up. Okay, so awesome. Thank you everyone for joining the webinar. I hope you learned something. Feel free to enroll in the course and really get this foundation on machine learning in C#. If you have any ideas about, I produce loads of courses, so if you have any ideas about what kind of courses I could develop in the future related to machine learning or other cool, sexy technology, please let me know. Go to the Facebook group, C# Architects, join the group, and then drop your recommendations in there. I would be really interested to hear your feedback. So yeah, thanks again. Also, thanks to our lovely co-host, Sansalis, for running this webinar and keeping everything organized. Sansalis, thank you.
Thank you, Mark. Thank you.
And that concludes the webinar. So thanks, everyone. We'll be signing off now.
Okay.
Thanks again.
Bye-bye, everyone. Thank you.
Bye.